welcome everybody. It's a great privilege for me to introduce and to chair this session, which is a debate. The debate is what is a solution to the measurement problem? I'm going to begin with a couple of clarificatory remarks as to, well, what is the measurement problem of quantum mechanics? And then I'll introduce our speakers. Then they go. Okay, so my introductory remarks, I've got to be very careful not to prejudice this debate. I won't take sides. I'll divide myself into two, one defending Carlo and the other David. Anyway, so what is the measurement problem of quantum mechanics? One answer to the question is, which explains the name, why is it called the measurement problem, is that it appears that quantum mechanics in its very formulation requires some statement, some law, some principle bound up with performing measurements or performing observations. And that seems very unusual. We don't normally have physical theories that come with axioms or principles or postulates which are at such a high level. So that's one way of articulating what is the measurement problem and why is it called the measurement problem. And a typical, if that is what counts as the measurement problem, a typical solution may be to try to reformulate quantum mechanics to avoid troublesome mention of measurement or observation. Now, that reformulation can take many different forms. Some are perhaps revisionary, some perhaps question whether quantum mechanics is a theory about physical things at all. Perhaps it's more of a meta-theory about how to update rational credences. So that's a general open-ended project of reformulation, if I can call it that. So another way of phrasing the measurement problem, and one that's probably the most popular among philosophers of physics, is to take a specific formulation of quantum mechanics, namely the Schrödinger equation, and to pose the question, this is a deterministic equation, let us suppose it describes reality, like other physical laws with which we're familiar, but then how to reconcile that with the apparent indeterminism that we see around us. So if that's the measurement problem, then solutions to it can take the form of perhaps revising this equation, the Schrödinger equation, or perhaps supplementing it with additional variables, these being the dynamical collapse approach and hidden variable approach, or some other way of understanding the Schrödinger equation which somehow accounts or explains indeterminism, despite the fact that the Schrödinger equation itself is deterministic. So a third class general approach to the measurement problem, which in a way can leverage off either of the previous two, is to shut up and calculate. So that's probably the most popular approach to the measurement problem, if you can call it that, among physicists. And sometimes it comes supplemented with appeal perhaps to Bohr's complementarity. That was particularly important in the early years, in the 20s and 30s, a sort of philosophical superstructure to the shut up and calculate, which enabled physicists to happily shut up and calculate. So that's another general approach. And then there's a fourth class of approaches which, for example, issue ideas like retrocausality, perhaps. I'll include the Aharonov two-vector formalism in that, or perhaps appeal to the Kramer's transactional interpretation, so-called, or perhaps quantum logic. So a sort of a ragbag of different approaches, none of which I think has really achieved a systematic, finished form. Okay, so now I hope I haven't prejudiced our speakers. They may take issue with how I've set it up, and that's great. But let me say a little bit about them. So Carlo Rovelli, who known to us all, I think, as one of the greats in the quantum gravity community, who speaks to philosophers often and well. Carlo is the author of his own interpretation, the so-called relational interpretation of quantum mechanics, which I'm hazarding a guess now. I would guess it's in the reformulation approach, but Carlo may correct me. David Wallace whoever it was the champion of the many worlds interpretation, but unfortunately he can't be here. But David will do even better. He understands better a little bit the way that Bert Drebin said he understood Quine better than Quine did. David, recent author of The Emergent Multiverse, Quantum Mechanics According to the Everett Interpretation. Carlo, I don't think your books need plugs from me. So welcome to our two speakers. A round of applause for both, and Carlo will begin.
Thank you, Simon. No, I don't take issue with any of the things you said. I'm happy with it. It's an honor being here among philosophers. I'm not a philosopher. Put my hands ahead. So I apologize for my philosophical shallowness, whatever. I'm a humble physicist. I'm very honored of you listening to me. But this is a problem that interests equally physicists, many physicists, and many philosophers. I'm just giving a 15 minutes, very short sketch account of the way I think about this problem. And I have chosen this title from the lab view to relational quantum mechanics. The lab view, the expression the lab view, I learned from your book, in fact. And in fact, I think it's a very clean and nice way of bringing up what the problem of quantum mechanics is. Because the way we study quantum mechanics in most textbooks of quantum mechanics, it works very well for the lab. I mean, you have a system, you make a measurement, you wait to make another measurement, and you compute probabilities between measurements. It's wonderful. But as soon as you want to take this logic to the way we think quantum mechanics could work, I mean, to describe what happened at different galaxies at the beginning of the universe, of taking this as the best dynamical theory we have at present about the universe. This lab view, based on observer, physicists make a measurement, doesn't work anymore. And what relational quantum mechanics is a way to somehow take minimal quantum mechanics as we learn in textbook and get away from this lab view, making it a little bit more coherent. Let me start by what I agree with David very much. I agree with a lot with David. We are both, I think we both considered ourselves children of Everett in different ways. Of course, like all the children, we disagree on who is has the right legacy, but certainly we are. One of the things that David says in his book, his wonderful book, by the way, is let's take quantum mechanics at its face value. This is probably the best thing we can do for a theory which has had such an immense empirical success for nearly a century now. Instead of, so the problem here is instead of trying to change it, modify it, add additional structure or whatever, just take the question of the theory, see the way the theory is actually working, and try to make sense of it as it is. And now the agreement ends, I would say, because I would say that this is the theory at its face value. So this is the face value. This is the face of the theory. So quantum mechanics is a theory which is based on some mathematical structure and its physical interpretation. So to say, the mathematical structure is an algebra, a non-commutative algebra of observables, of variables, of quantities. The main things we are talking about here are quantities. And allow me, sorry, Simon, to say that what we are talking about is quantities, not things. Quantities being Q and P, the position and the momentum of a particle of an oscillator, and functions of Q and P, the Hamiltonian being a function of P and Q, or A being any quantity, say, I don't know, the angular momentum or something, or whatever you want, which is a function of Q and P. So this is an algebraic structure. It's very similar to classical mechanics. In classical mechanics, we have variables. They take values. The difference is that, the key difference is that there is an assumption about the non-commutativity of these variables. You can multiply P and Q, but P and Q is different than Q and P. And this is captured by this main equation, which I would say is the main equation of quantum mechanics, PQ minus QP is h bar times the imaginary unit. And then there's a dynamical equation, how things evolve in time, which is in terms of the Hamiltonian. If you know the Hamiltonian as a function of Q and P, you know how the things evolve in space and time, because you can evolve any physical variable A itself a function of Q and P. Now this is a math. How to relate this to the values of the observables? How do you relate the elements of a non-commutative algebra to the values which are real number? Well, that's the first key point of quantum mechanics. The possible values that a quantity can take are in the spectrum of the element of the non-commutative algebra of the corresponding quantity, or the eigenvalues in simple words. And the second, I'm not giving the full mathematics here, I'm just giving the sketch. The second is that if a certain quantity capital B has a certain value little b, then the probability that another quantity capital A has a value little a is given by a certain formula, which is essentially a formula written here that you can make sense in terms of sister algebra and the structure of the algebra. Now the point is that this is quantum mechanics. And I want to make it a little bit stronger rhetorically. This is the theory. This theory, quantum mechanics was invented in 25, not in 26. It's important. And was invented by these people. In fact, there's the first paper by Heisenberg, marvelous paper by Heisenberg, in which essentially he says, get rid of a lot of sort of simplify your ontology, not increase your ontology. And then developed by a sequence of paper by Heisenberg himself, Born, and Jordan, a beautiful sequence of paper which have everything which is in modern quantum mechanics textbook, have the angular momentum, have worked out almost completely everything. And independently by Paul Dirac, of course, who was inspired by the paper by Heisenberg, who got this, essentially that equation right, and soon got to write this book, 30s, a few years later, with basically quantum mechanics we know together. I'll say in a moment why I insist on this historical thing, but first let me say that there is something to add to the physics, which is where the problems come in. When is it that a quantity take a value? And that's the problem of the measurement, the measurement problem, I'll say in a moment. So let me, I'll come back to this. The value is actualized and realized in interaction with another system. So the value of a system, a variable takes a value when interact with another system, and values are relative to this other system. And values relative to system 2 are not value relative to system 3 and vice versa. I'll come back to that. I just want to anticipate to have the full story. So what distinguishes this from classical mechanics? First of all, they're probabilistic prediction, not deterministic prediction, but most important is discreteness. Generically, spectra are discrete, or more precisely, any quantities that sort of separate state one from another in a finite region of space has discrete spectrum. And discreteness is at the core of quantum mechanics. The quantum mechanics is about discreteness. The light is made by photon. Angular momentum has just two components, up and down. The spectra of the hydrogen atom of the energy of a harmonic oscillator is discrete. Yesterday, in Simon talk, there was the quote by Planck. The basic assumption is this discreteness of the packets of energy. Quantum mechanics is about discreteness. It's a discovery of discreteness of the world. And then there's a relationality on which I'll come back in a moment. Now, why I said that? Because 1 year later, in 1926, Schrödinger came out with a Schrödinger equation and this funny function here, okay? The quantum, which evolved in modern terms as the quantum state, an element of Hilbert space, and raised the hope that now we have understood what we're talking about. We're just talking a differential equation and things we physicists with classical familiars are familiar with. I think this has misled a lot of the discussion of quantum mechanics. And let me say how does a physicist address a new quantity that comes in a new theory which is successful? How does a physicist ask what is the physical interpretation of this quantity? There is a simple strategy, which is the new theory should have a limit down to the theories we know well. So you take this quantity, you see what becomes in the limit, and you understand what this quantity is. So let's do that for the Schrödinger wave function. Well, in the limit, we know what the limit in which classical mechanics comes out from quantum mechanics is when you can consider action small, h bar small. So you take the limit for h bar small, and the wave function is proportional to the exponent of the Hamilton-Jacobi function, which in fact satisfies an equation, which is a Hamilton-Jacobi equation, which is the classical limit, so the Eichel approximation of the Schrödinger equation. So we know exactly what psi is, has the same ontology of the Hamilton-Jacobi function, or the Hamilton function if you want to be more precise. And what is the ontology of the Hamilton function? Well, we know very well what's the ontology of the Hamilton function. I can have a pendulum, or can do classical mechanics of this, and I can write the Hamilton function. The Hamilton function is diffused all over this room, but nobody would give any ontological weight whatsoever to the Hamilton function, right? The ontology of the Hamilton function is nothing at all. Just a calculating a way for this pen being here or being there. And that's what the Schrödinger equation and the Schrödinger wave function, or more in general, the quantum state is about. Now, Schrödinger himself struggled with that. Schrödinger is one of the deepest thinkers in this field from the very beginning, I think. And this is a quote from this marvelous book that he wrote much later. He says, the inventors of wave mechanics, himself, who else? Okay? So Schrödinger is talking about himself. The inventors of wave mechanics indulged for some times in the fond hope that they had paved the way of return to a classical continuous description. Continuous is the key word here. But again, the hope was deceptive. Nature herself has seemed to reject continuous description. And the gap here in the context, if you read, is really the quantum leaps of Bohr, the quantum jumps of quantum mechanics. Quantum is about quantums, discreteness. Eliminated from the wave picture, have withdrawn to the connection between the wave picture and the observable fact. They later are not in one-to-one corresponding with the forward. The world is discrete, is not the continuous of the continuous evolution of the state. I have moral always from Schrödinger making the point about discreteness, but I don't want to go too much into that. So this is quantum mechanics. So let me go to the key point. There is this caveat. So why there is this caveat? Well, because in the textbook, all what I've said is written in the textbook. Okay, standard textbook of quantum mechanics. That's what you read in quantum mechanics. But then, when do variables take value? When you measure them. That's what is standard, which means that, there's a physicist with a white thing in the laboratory to make a measurement. And of course, this is the moment in which we have a problem, we have the lab view, we have to come out from it. So I come now to what I think is a possible solution of this problem, which is a simple one, and is the following. If we simply replace the notion of measurement with the very general notion of interaction, so if you accept the idea that values appear, so variables take value anytime there is an interaction between the system and another system, when the interaction is such that the influence on this other system depends on that particular variable, okay, then we free ourselves completely from this dependence on laboratory physicists, subjectivity, consciousness, or whatever. It's just a simple interaction. And we can do that. This is a viable solution, provided, and this move is necessary because otherwise we destroy interference every time there is an interaction, provided that we restrict the value to be a value relatively to the system with which the first system has interacted. So we accept that values with respect to the system 2 and values with respect to 3 do not determine one another. And this is a step from the lab view to the relational quantum mechanics. Now, what is a relational property? A relational property is not something complicated. the prototypical relational property is a property that doesn't pertain to one system, but pertain to one thing, but pertains to two things. The physics is full of relational properties in gauge theories, in general relativity, in wherever. And the quintessential relational properties is velocity, right? An object has no velocity itself. You need two objects to talk about velocity. Once you have two objects, there is a relative velocity. And if you think for a moment, position has no meaning in classical Galilean Newtonian physics, properly understood as we understood it today. So position is a relational. The difference between classical and quantum mechanics, where is it exactly? It is in the fact that in classical mechanics, if you know the position of the velocity, say velocity of this with respect to that and this with respect to that, then you know the position of this with respect to that. Not so in quantum mechanics. What happens in quantum mechanics is you have to disentangle you have to get up with the idea that a farther external observer sees everything, has all the values with respect to this observer determine the relative values of the system one with respect to the other. If you do so, I claim, and this is a long discussion on which I'm not going, that you get a consistent, coherent interpretation of quantum mechanics. Now, last slide before the summary. Why isn't everybody jumping and say, oh yes, yeah, that's obviously the solution of the problem of quantum mechanics? Because every solution of problem of quantum mechanics, and that's why we're debating, comes at a price, at a cost. And I think it's wrong to say that there are no solutions to the problem of the interpretation of quantum mechanics. I think there are many solutions, and many that after a long discussion have been, I think, understood to be coherent. This is a list of some. It's not meant to be a list of exhaustive list. Each one has its own cost. If you start from what is in the textbook, there is a problem of what is observable, what is a measurement, which you can resolve it, going to the relational interpretation which I just discussed, which if you want is just making Copenhagen democratic, right? With respect to every system, the rest of the world is quantum mechanical as described by standard quantum mechanic textbooks, just making Copenhagen democratic. What is the cost? The cost is that you have to accept it's a relational character of reality. Not just velocity requires two systems to be defined, but any property of any contingent property, the things that change with phase space, not the mass of an electron in non-relativistic quantum mechanics, but any contingent property of a system take value only with respect to another system. And the claim is this is coherent, it stays together. But of course it comes with a cost, because you give up the idea that there is a unique objective description of the world as seen from God outside the world, in which everything can be said about everything which happens in the world. So I wouldn't characterize this as a non-realistic interpretation of quantum mechanics, but certainly there is some weakening of strong realism. But strong realism is meant that what is true with respect to a third observer exhausts what is true about a composite system. There are other coherent solutions, like Bohemian quantum mechanics, a perfectly coherent solution. It comes with own price. I don't want to describe the price of any wall. It's many walls, and the advantage of it, just ask David. He will argue for that, or physical collapse, and so on and so forth. Last remark is that the different prices that you pay for each one of these views of quantum mechanics have a different cost depending on your philosophical assumption, prejudices, position, of course. I mean, whether you're an empiricist or whether you're a realist or whether you're an idealist or whatever, you tend to give a very different weight to this cost, and vice versa. Whatever are your philosophical general stance, you have to deal with the strangeness of nature and see how to make sense of the stranger of nature within your philosophical view. So there's a back and forth, I think, between the technical problem of making sense of this set of equations and its empirical success and the general philosophy that you have, which is, I think, what makes this problem so interesting. I mean, I think the clearest attitude is to keep in mind that there are all these possibilities, and each one comes with its own cost, because the discussion is moving ahead, we are clarifying, and physics is moving ahead. We're doing quantum gravity, we're doing quantum cosmology, and so on. And at some point, some perspective will be more fruitful than some other one. One of the reasons I like this relational interpretation is because I think it's particularly good for quantum gravity, which is my own field. So that's my summary. First of all, the face value of quantum mechanics is not, the main point I want to hammer in a sense, is not a wave function of Schrödinger equation, is not a Hilbert space in a unitary evolution. It's wrong to say, okay, quantum mechanics is a Hilbert space in a unitary evolution, now let's make sense of it. For a physicist, whether he's in a laboratory and a theoretician, quantum mechanics is about eigenvalues, it's about discreteness, it's about quantities, not about states, Hilbert spaces. This is abstract mathematics. It's about quantities that take values in interaction, and quantities are represented by algebra functions. The physical content of quantum mechanics is discreteness, probabilities, and relationality. The central idea of relational quantum mechanics is nothing special is counted to count as measurement. Any physical interaction is a measurement, but the values that variables take are relative to the interacting system. It doesn't need to give up realism, and as I said, one way of putting it is to make quantum mechanics democratic. I guess I'll stop here. I just had, just in case anybody's interested, a list of references on relational quantum mechanics, which I think is still not the most known interpretation, especially in Oxford, which is the Batana, we say in Italian, the cave of the many worlds.